Hi, my name is Ajay. This is Lab 5 for Modern Physics 1. So for this lab, my experiment will involve a little basketball that will be thrown with both x and y initial velocity. So we'll be analyzing how those change while an object is in free fall. So we'll be observing how gravity affects the motion of a falling object and see how the x component changes, because we haven't really covered that in a lab. So the concepts we're going to be covering, we're going to be covering position, acceleration, and a little bit of drag. That's just more of the discussion later. So the results of this lab: in perfect conditions, gravity causes an object that is falling to accelerate at a constant rate, which we'll see later, while the x component of the velocity is constant throughout the fall. So the concepts we're going to be covering are velocity change due to gravity, which is the acceleration due to gravity times change in time. Our position formula is equal to the final position. Our final position is equal to initial position plus our velocity times our change in time. And then if we fill in our acceleration, we get this other final position. And then here are our experiment in initial conditions. So for this experiment, the system that we have chosen is the ball, and then the surroundings is the hallway. Even though we have a hand pushing the ball, we're going to pretend like that's just a force or initial velocity that the ball carried, so we're just going to disregard that. So initial conditions, these are calculated from the tracker. Negative 2.775 x component for initial velocity, and then 1.919 for the y velocity, and then our initial position is 2 meters above the ground. So then our forces acting on the ball are gravity and drag. So here's the video. So over here on the right side, we can see both the x position and the y position. Now, the x position, if you look after around 0.1 seconds, you'll see that it's a constant slope downwards, indicating that the x velocity does not change throughout the experiment. That's because there are no forces acting directly the on the ball in the x direction. Even though there is drag, it is very insignificant in this process due to the shape of the ball. But unlike the y, where it starts a little bit above 0, goes up, and then comes back down, this is due to the acceleration due to the gravitational pull of the Earth. So we can see that from this graph that it is accelerating with a constant velocity. So I calculated this in a GlowScript model. So over here, the velocity versus time graph, this is actually our x velocity. As you can see, it's a constant line it's a constant slope for the line because the change in velocity is the same because it's just a constant gravitational force. But the position, however, that increases the slope, increases its steepness as time goes on because it goes up and then accelerates downward. So it's going to be going its fastest near the end of the ground. And then this black little graph at the end, this is our computational model of what the ball's motion should look like. So from this point, we can see that the yellow, that is technically our origin of our axes. And then we go 2 meters up, the ball is thrown, and it goes up a little bit first because it does have an initial y velocity, but then it goes down due to gravity. It'll accelerate towards the ground. And since we gave it an initial x velocity, the velocity will stay the same throughout the experiment, and it will proceed in the left direction. So discussion. So possible sources of error for this. One, the video is not taken perfectly still. So if you do look in the graphs, there are some minor discrepancies where the x velocity is not exactly perfectly linear. It should be linear just because there's no forces acting on the x. And also, this is not a perfectly isolated system either. We need to account for wind, breeze in the hallway, which is drag. So the object was not affected by drag as much as we expected. And then the object had an initial y velocity too. That can kind of mess with some of our calculations if we don't do it correctly.